So I'm Andrea Vedaldi, and I'm a professor of information engineering or engineering science in Oxford University, where I work in computer vision, which these days means machine learning. Okay? So what I want to talk to you about today are three topics: universal, unsupervised, and understandable image representations. And in fact, that was the original plan. Unfortunately, I do not have enough time to cover all these topics, so you're going to see a selection of those. But before I dive into that, I would like to give you a little bit of introduction and motivation. So I think an interesting question is, how can we get AI to have an impact on people? And I think there are two clear answers. One is by solving what we could call horizontal problems, say something like autonomous driving, searching the internet, social networks, and medical imaging. And there's a question mark there, not because this is maybe not important. It is very important, but because it might not be all that horizontal, okay? The other way we can help people is by solving what I call vertical problems. What are those? Those are problems which are much more specific to small user communities or maybe individual users that require to have intelligence which is customized to their needs, okay? So just to give you a few examples of that. So one set of problems we work in Oxford are problems connected to digital humanities. And that means, for example, being able to run statistical analysis of ancient illustration in books, text in manuscripts, Greek vases, paintings. And here you can see one example of how this was done before AI, before computer vision. So someone would just sit there using this contraption, would take 2 pages of a book, maybe 2 illustrations, you want to compare them, and you do that through a set of mirrors. So quite inconvenient. What we want to be able to do is to take all of these problems and make them much more convenient to solve and solvable at a much larger scale. So not something you can do manually like that. Here's another example. This is counting penguins in Antarctica. So within each box here, we're counting the number of penguins that appear. And that's because it's useful for zoologists in order to build statistics on the life of these penguins, which is actually very important in relation to climate change. And of course, you could do that manually, but it's very tedious. So this is thousands or at least hundreds of hours of videos. So if you can do that automatically, then you can do these experiments at a much larger scale and much more cheaply. So very interesting, but very, very narrow, okay? More examples come from biology, zoology, particular area of medical imaging where you may be studying a very specific disease that not many people have, material science and all that. So you see here an example of an application that we have built in collaboration with the material science department, in which the goal is to count how many of these flakes, these are actually crystals, I think, of molten metal, which are condensing. So you want to count how many of them are forming over time. So you see here the process done manually and the process done automatically, and you see that there is a very good correlation between these two curves. The advantage of doing this automatically is that, again, you can do it at a much larger scale, and if you can do that, then you can do new science and publish in Nature, which you would not be able to do without these tools, okay? But again, this is very, very specific, very, very tiny problem that requires a lot of engineering, on our part in this case, to be able to solve. So what is the problem here? So we have technology like deep learning that can do all these things quite easily, or at least a lot of these things quite easily. But then deep learning per se has a very significant bottleneck. And the bottleneck is the fact that it requires loads of data for building these models. So deep learning, in computer vision at least, it exploded with the introduction of one such very large data sets. You have heard about this before. That's ImageNet. It contains 1.2 million images, which were manually annotated. But these days, there are many other data sets which, in a certain sense, they are even more impressive. So this is AD20K. That's much smaller in number of images, but the annotations are much more complex. They are dense at the level of individual pixels. You have something like visual genome, 100K images, in this case annotated with objects and their relationships, so much more expensive to collect an annotation for an image here or there than it is in ImageNet. And then you also have another example from Google, in this case, open images, 9 million images with 28 million annotations. So these data sets are gigantic, and this is what we need these days to make computer vision work, or deep learning work for these applications. So the question is, will this guy label 1 million images or not? What do you think is the answer? Silence. Okay, of course not, but this is the problem we have, right? So we have a lot of people that would benefit tremendously if we were able to deliver AI which is customized for their problems. But we cannot do that because we do not have the resources, since the problems are so specific and so small in terms of impact, that it justifies allocating them to solving them, right? So we could solve them, but it's not economically sustainable. On the other hand, if we did have a technology that can solve all these problems, then the overall impact, summed over all these millions of specific problems, together would be, I think, much more massive than trying to solve what I called before horizontal problems. So the question is, in order to unlock the real power of machine learning, I think we need to address the problem that we need to change the learning paradigm, so we don't need to have this 1 million images annotated. And the question is, how are we going to do that? So I usually break what I think are three important aspects of these problems into three parts. So universal representations, this is about building models which are able, out of the box, to solve problems without you having to train them specifically for new tasks. And these have to be universal models in the sense that they have to be very generic. They are just as applicable as vision in human. You don't need to train your brain from scratch to become a doctor. Of course, you need to do some training, but that's probably a much smaller amount of training that you have done during your lifetime in order to be able to learn to see, okay? For the purpose of processing images, of course. Of course, becoming a doctor is actually very hard. Then the other topic which we're going to spend most of the time on is unsupervised representations. So how can we train networks without, in fact, manual supervision, or with cheap form of supervision? And then the last part is related to these two, although in a less obvious way, and that's about understandable representations. This is key in order to be able to build trust in the models that we are learning. And therefore, well, giving people a peace of mind that if they use those models, they're going to do something sensible, as opposed to get random results, which is probably not something which is very acceptable in most cases. Okay? So as I said, if I had maybe 2 hours, I would go through these three topics, but because I don't, I will start by discussing this part instead. Okay? So unsupervised representations. I will make available slides which cover all the three topics online if you're curious and you want to have references about those as well. Okay? So, unsupervised representations, what this is all about. Again, we want to train deep networks. It's very easy in most cases, but not always, but in most cases, it's actually quite easy to get lots of images. What is very expensive is to collect the corresponding annotations. So, what we want to do is to just get rid of those. Okay? So what we want to do is to find ways of driving or extracting a supervisory signal from the images alone. And this is called self-supervision. Self-supervision means we're going to find a way of extracting a supervisory signal from the raw data without having a human annotator that tells us what to do. Okay? Now this part is further broken down into three sections or chapters, if you like. So self-supervised features, self-supervised structure, and then the deep image prior. And I'm going to start from the first one. Once I get to these points, it will be so to the point of discussing those, it will be clear what those are. Okay? So self-supervised features. What do I mean by that? So in this part, what we're going to try to do is this. We're going to try to find pretext tasks. So these are problems which are not very interesting per se, but for which you can have cheap annotations. Okay? There's a pretext in the sense that we're going to solve them, not because we want to solve those problems specifically, but because we can get cheap annotation for them. And in the process of solving those problems, we can train an encoder network here that we can then transfer to a task that we actually want to solve. For example, classification in ImageNet, if that's something that it is of interest to you. Okay? So again, I'm going to repeat. So the strategy here is going to be to search for problems that are not so interesting, but for which we can get cheap supervision, and that can be useful to train a network that then can be used to do something more interesting later, using, at this point, far less manual annotations. Okay? It's like playing games. You're playing games because they are fun, but really, biologically speaking, fun is probably something that stimulates you to do something which is useful in order to train your brain or your body. So I'm going to discuss in particular three ways of building self-supervision into your network. And these are perturbations, using motion, and using multiple modalities. So let's start with the first one, which is perturbations. So this is what training a deep network, if you have supervision, looks like. So first of all, you have an image X that is mapped to some label Y. which generally lives in a different space, by a human annotator, this guy here. Okay? In practice, you're going to have probably a few hundred or a few thousand Turkers doing that for you at the scale of 1 million images. Okay? So not very good. Then what we want to do is to train a model, a deep network here, that is able to predict the same label. And we want this deep network to be able to do the same as the human annotator. Okay? So this is also called a commutative diagram because you get to y from x either following this direction or following that direction. Okay? And here, it really is just identity function. It's just to say that the predicted label should be the same as the estimated label there. The ground truth label there, which is determined by a human annotator. So this is what we do normally. We don't want to do it because this guy is too expensive. We need to pay him too much. So what's the idea? Of course, we have deep networks, so why don't we simply replace this guy with a deep neural network? Can we do that? Obviously not, because learning this auto-annotator isn't any simpler than training the model we want in the first place. So this is not really a feasible solution. So what can we do instead? Well, here's the first idea. We're going to use perturbations. So what this means is, instead of starting from an image and getting an auto-annotator or a human annotator to give us a label, we're going to start from an image as a label. That's a reversion of roles. Okay, it's quite interesting. And then through an automatic process, we are going to generate a perturbed image. Then what we're going to learn is a network that, given the perturbed image, tries to reconstruct the image we started with. Okay, so it tries to undo this automatic process, which introduces a perturbation in the image. Now, this is pretty abstract, so let's see a concrete example of that. So here's how this might work in practice. So I get an image, and then my perturbation process means I'm going to delete half of it, so the perturbed image is the same as before, except that half of the image has been deleted. And now what we're going to do is we're going to train a deep network here that tries to recover the complete image from this half. And again, the idea is that the network should make this linked the identity in the sense that the restored image should be the same as the image you started with. OK, so why do you think we do that? That sounds a little crazy, right? Why do you think this might be useful to train a sensible network? What's missing here? The bottom of a bool, right? Now, presumably, if you know about bool bottoms, then you have learned something about bools in general. Okay? So this is like a game the network is playing for which solution should require the network to learn something about the semantic content of the image, where semantic means the existence of an object like a bool in it. Right? Now, if you think about it, you can download very easily 1 million or even 1 billion images like this, or genetic images from the internet, and then you can set up this learning process completely automatically. And if the network can solve these problems, maybe it learns about the object in the images. Maybe. We don't know. Okay? Now, if you want to see how this is set up in practice, so we start with a bool image. Then there is a data generation step in which we erase half of it, and this is, of course, automatic. Then we learn an encoder-decoder network, as we have seen in the previous talks several times, that is going to solve the pretext task of reconstructing the missing half. And then we're going to set up a loss here, which compares the output of the network to the input and tries to minimize the difference. Okay? Very, very easy. And again, the reason why we do that is because in order to solve this problem, hopefully this encoder and decoder network will have to learn something about objects. And if we succeed in doing that, then maybe we can use this encoder then to recognize bools in images with the addition of a very small amount of manual annotations, which amount to just giving a name to this object effectively. So which kind of perturbations can we use here? Now, this is actually a very active field, and people have been playing with lots of different ideas, so it's actually quite interesting. And several of those might translate directly into medical imaging. So this is maybe one example that doesn't, and also well. So this is decolorization. It means you take a colorful image like a parrot, you remove color, and then you train a network which predicts the color that you have removed. Okay? You can erase a bit of the image, as we have seen, or maybe you can scramble the image. You can rearrange different bits, and now your task is to solve the jigsaw puzzle and reconstruct what the image should look like originally. Okay? And you can come up, I'm sure, with different ideas on games that the network can play. that do not require manual annotation, but that might be useful for the network in order to learn about semantics in images. Just you need to use a bit of creativity there. But is this all good? Well, not really. So one shortcoming of this kind of approach is that, well, you're learning a deep network here, but that deep network does not operate on the image that you would like to process, but is operating on a perturbed version of the image X. For example, this could be a decolorized image or an image with a hole in it. So yes, you're learning a deep network that maybe learns something useful about objects, but at the same time, is learning that starting from an image which does not match the statistics of images you really want to use. So there is already a shortcoming in the setup. So what can we do in order to solve this problem? Well, maybe instead of trying to generate this image X from an automatic perturbation of Y, we can try to seek for a source of images which are related somehow, and then directly try to predict the second image from the first one, and use that as a pretext task. Now, this is again very abstract. Let's see how this might work in practice. So in practice, you might have a video sequence. Then the first image here could be the first frame. That's X. Y is going to be the last frame. And then you want to train a network which tries to predict what's going to be the future. Okay? And ideally, you would like the prediction to be perfect, so these two things to be equal. But in fact, because of reasons we're going to see in a minute, you can expect this to look quite bad because it's so hard to solve this problem. But in principle, this is how you can get two images that are related, in this case related through time, and you can use those to play this game and train a network from that without supervision. Just need videos as input. Oh, manual supervision anyway. But we can generalize this even further. So in general, we can search from some common cause, something abstract, and then we have two sensors. Could be a camera times 0, camera times t, or could be a sensor like a camera as well as an audio sensor or something else that generates two pieces of data, X and Y, which are somehow related. And again, we're going to play this game of training a network that can map X onto Y. We know that that's meaningful because, well, these things have a root common cause. So we might try to seek that. Okay? We want to regress that effectively by learning this deep network. So here's an interesting example. This is a little video of someone playing an instrument. And one thing we can do is to exploit the two modalities we have here. So we have an image, we have audio, and we can train a deep network to try to predict the audio from the image. Okay? So this is quite interesting. It's not done like this in practice. We're going to see later how it is done really. But it's interesting because it's exploiting two very different sensors which are almost orthogonal, video and audio, and it's trying to correlate them to try to find a common abstract cause which causes these two very different things to actually be highly related. Okay? So that's another way you can get supervision. Before I move on and describe how this is actually done, here's another example of supervision. Okay? So you might recognize this guy, but that's not really the point. So what they would like to tell me is which one is the right image. Yeah? The second. Okay. The fourth. This one. Yes, because you want to sleep. I know that. You're very tired. But if Giovanni is not tired, probably this one would be the right one. How do you know that? Because of gravity. Okay? So gravity gives us directionality. If you were born in space, probably any of those images would be a fine image of Giovanni, right? But because there is gravity, there is a bias that humans have that they're standing upright, and when they take a picture, that bias is transferred onto the images, okay? Now, therefore, if you take any data set like ImageNet, a hidden bias is the fact that all images are upright, or most images are upright, 99% of them, okay? And now that's like a hidden label, and you can set up the problem of, you rotate the image randomly, and then you have to guess with the network which one is the upright one as a pretext training for learning the network, okay? And now this is not exactly unsupervised. The supervision is there in a bias that is implicit in the data set. But there are many similar biases in the way that people take pictures that you could try to exploit in order to train deep networks. Surprisingly, this is one of the methods that works the best for self-supervision. It's very, very simple, but very, very effective. Okay, just train a network to tell you which one of these four is the upright image. That is actually quite powerful for pre-training features. Simple, but very effective idea. Okay. So this is what you can do. And in fact, you can do many more things, but there is no time to cover all of them. Now, let's see how you set up this problem a bit more formally, and so that you actually go home and try it out on your medical data. Okay? So these are cues that you can use for pre-training networks. Here are methods that you can use to set up the learning problem. So we're going to focus on those 4 things now. So one thing that you might have noticed is that all these problems have one shared characteristic. They are generally all very hard. What does it mean? They're hard because they're very ill-posed. So for example, if I give an image like that, well, this is a plausible colorization of your parrot, but the parrot could be blue. Who knows? So the answer is not unique. If I give you future frame prediction, it's the same, right? So this is an input image. Yeah, maybe this is a plausible feature, but there are many other variants of that image that might fit that as future frames just as well. So you don't really know. This is maybe even worse, right? So if I give you an image with someone playing an instrument, yeah, you kind of know what this is going to sound like, but you cannot really reconstruct the specific waveform. That's just impossible, too hard. It's just ill-posed. There is not enough information here to do this mapping. So what can we do instead? Well, one approach is, all right, so I cannot predict y specifically, but what I can try to do is to predict a reconstruction here, which is a distribution over likely outputs. Okay, so you have an ambiguous output, you model that for probabilities, you are happy. You just need to design a network that instead of producing a single output, it produces a distribution over outputs. Okay? So for example, for future frame prediction, POY might encode the fact that, well, many different future frames are actually possible. Now, this is an interesting idea, but it has shortcomings. Usually, building a model that can predict the probability distribution over images is actually quite challenging. Fortunately, there are methods that can do that, like GANs or variational autoencoders, and you have seen maybe 3 times already about them, so I don't need to cover them, fortunately. But nevertheless, although there are solutions there relatively complex, and I should remind you that we don't really want to solve these tasks per se. This is just a pretext for training a network. So maybe if we can simplify the problems in some other ways, it just simplicity will be gained, and we're not going to lose anything in terms of learning the network, which is what we really want to do, or pre-training the network, which is what we really want to do. Okay? Otherwise, you can try to come up with a probability model which is very simple, but then maybe that's not really going to help you in terms of modeling these ambiguous features. So what else can you do? Another very simple thing you can do is to constrain more the prediction task. Ask your network to predict less. For example, you can take a video here. You can perturb it by reordering randomly the frames. And then you can task your network with not predicting the frames from scratch, but rather just reordering those in the correct sequence. Okay? So you want to train a network which somehow captures this notion of causality that you have in videos. Now, where is the simplification here? Well, the simplification is that here, your network is only estimating a permutation over frames. It's not really trying to predict the pixels because it's already given the information of what the images have to look like from the outset. So it's much, much easier task. Okay? So reordering is much easier generation. And of course, you can, we have seen already an example of that. If you take an image and we scramble the bits, well, that's another example of reordering, although that's done in space as opposed to be done in time. Okay? So that's another approach number 2. Here is approach number 3. Okay? So this is one which I found quite intriguing, and there are a few papers that are exploiting it, although not that many for now. The idea is, all right, so I have 2 related pieces of data, like say past and future frames, but I'm not really interested in recovering y. I'm just using this as a sort of a gym, as a training process. So maybe instead of predicting y as a whole, or all the information that y carries, I'm going to predict what I define here as a character of the full data. So some property of y, but not y as a whole. Okay? What I need to do in order to implement this is to replace this that was the identity before with an arrow which embodies what I call here a marginal loss. Marginal loss can be implemented in 2 ways. By the way, this is just in quotes because this is not official terminology. I'm just trying to put names to things that people have not defined very well in the literature just yet. So what do I mean marginal loss? Marginal loss is something that matches y to y hat, despite the fact that y hat is only capturing some partial properties of y. You can do that in 2 ways. Either you can take y and project it to simplify it, or you can just marginalize out some variable that taken y hat can reconstruct y. So here, that latent variable is eta. 2 ways of setting this up. Very abstract. Let's see a concrete example. So in future frame prediction here, instead of trying to predict the future frame, what I can do is try to predict a mask that tells me what is actually going to change in the image. So now the problem I'm going to try to solve here is not the one of predicting the pixels as they're going to be in the future. I'm just going to try to predict which subset of this image is actually going to change in the future. So it's a much, much easier problem. And then I can match that to the output of a video segmentation algorithm, which differently from this network sees the entire video. Okay? So this has a much easier life in determining what this region should be. So it's actually almost trivial, not quite, but almost by comparison. And then you can try to match these two things. Okay? So you try to predict essentially what we call in computer vision, if you like, motion tubes. So regions that move coherently together. Okay? So here's another way you can implement something like that we recently did. So you take a video like this, you extract optical flow. You have seen a lecture on optical flow, so you know what it is if you forgot. So each color here represents the amount of motion you observe instantaneously on the central frame there. Okay? And so you see here that the baby is somehow moving, and it's moving differently from the background. And maybe this is something you can tell from the images as such, right? But it's actually hard to predict exactly how the baby is going to move if you only have a single frame as input, which is what the deep neural network is going to have, right? So the damage or perturbation we're going to apply here is that we're going to extract a single video out of a sequence. And now maybe we know that this guy is actually likely to move, but it's very hard to say exactly how from a single frame. So what we can do here is we take pairs of pixels and we compute the similarity between the flow vectors. So we're only going to tell whether these pixels move together, they move in a similar manner or not. Then we take pixels in the input image, we compute their similarity, and if two pixels are deemed to be similar, we expect their motion to be similar as well. So this should, in a certain sense, segment objects in an image because they're likely to move in a coherent way in the video, although the network doesn't actually see the video. Okay? And then there is a comparison here, a loss between kernel matrices, which are going to try to match the similarity of motion fields, vectors, and pixels. Okay? All right, so that's one way you can set this up. That was approach number 3. Now let's go to approach number 4. This is also fun, and I have some audio for this. So here are 2 videos. The first one is going to play now, I hope. How do I do that? Yeah, like it's actually both of them are playing. So, all right, so this is a dude playing a guitar and a dude playing percussion, but it's not very good, so it just gives up. Okay? And now I'm going to play the audio. Okay, which is which? Okay, so this goes with that, and that goes with that. Okay? So here, where the problem we are trying to solve is not really to predict the specific audio, which would be very hard. We know that the audio of this guitar is either this or that. We just have to tell which one is the right match. Okay, so we're going to look for correspondences as opposed to generation. Now we can set this up formally. So as a step towards that, it's going to look something like this. So we have 2 videos. We extract a frame, or in this case, also just the video part of the video, not the audio. That's sensor number 1. Sensor number 2 is going to be the audio. Here we have a switching variable that is going to pick either this audio track or that audio track. So this guy here is either a copy of this guy or that guy, depending on this binary value here, which is sampled with a 50% probability to be 1 or 0. And then you have a visual network that encodes the visual information. You have an audio network which encodes the audio information. And then you have a predictor which compares these 2 embeddings, which now live in somehow a shared space. And it has to decide whether the video matches the audio or not. Okay? That's actually a rather interesting way of doing things. And this, I think, is very applicable to medical imaging, although you might not have video and audio very often, but you do have many modalities. So you can think of this as 2 different modalities. Okay? And you can use that a similar contraption for training. So if now we abstract this slightly more, we have 2 root causes, Z and Z prime. These are sampled from some distribution of causes, but they are independently sampled. Then we break these 2 into sensor reading number 1, sensor reading number 2. From Z prime, we only apply the second sensor, and then Y can be the output of this guy. So it can be estimated from this guy or from that guy, depending on the value of the switch. And then your network has to tell which is which. Okay? And once you abstract it like that, you can play with what Z prime and X and Y are, and you can frame many different training procedures like that. So I looked at that and thought, well, this is actually fun, but can we do something which is a bit more principled? Well, maybe we can. So if you think about it, one thing we can do is, all right, so we can have a common cause here, Z, and we have 2 sensors that are going to split that data into somehow independent data streams, X and Y, and then we're going to try to learn two networks, phi1 and phi2, such that the output of this network is going to be mutually highly informative. Okay? So this is very similar, but a little bit more formal than solving the problem that I showed you before. And then it leads to a very simple formulation in which you want to maximize, as a function of your network parameters, phi1 and phi2, the mutual information between the output of these two models. And that leads to a self-supervised formulation, which is actually also rather general. So here's a concrete instantiation of that. You can take an input image here. The two sensors, in this case, amounts to extracting nearby patches in the image. The networks are going to classify those patches in one of k classes. This is just clustering. And then you want to maximize the mutual information between the clusters which are being activated, given these two patches, which are related by the fact that they are collected nearby. If you do that, then, well, you can learn to cluster images, or you can learn to segment images like that. So here you see a traffic scene, and you can see in this column here, the network trained to cluster pixels, and is automatically learning about things like buildings, roads, and trees, say. Now, this is a bit preliminary, so it's still debatable whether this is a better approach compared to the more, if you like, hacky one of using this sort of contrastive approach of having the binary variable switches or not. But I think, in general, this can be a quite nice area to explore further. Okay? All right, so this is a very quick overview on how you can, these days, train self-supervised features without using GANs or relational autoencoders. I want to move to the next topic, which is, well, let's try to do something more here, not just learn features, but learn structure of objects in images. So here's an object. This is just a fox, and it does some trick. Do you guys know what this guy is doing, by the way? Fishing. It's hunting. It can sort of smell or hear critters under the snow, so it's just trying to catch them. Okay. Anyway, so you see that, and you could say, okay, I'm going to take a lot of these videos, and I'm going to learn some implicit features. So maybe these are useful to recognize foxes. Fine. But suppose we want to be a bit more ambitious than that. So if you look at these videos, in your head, somehow, there is this concept of an animal which has a very well-defined shape, is deformable, and is imaged under a very specific viewpoint. And so this very complex idea of what you're looking at emerges in your brain somehow automatically, right? Now it's easy because you have seen lots of those things in your lifetime, but somehow your brain learns to do that when you're a baby completely automatically, all right? So can we do that with deep learning, or in general with machine learning? I don't know that we have a complete answer yet, but I'm going to show you what we did about this problem. And I think we have made some reasonable progress so far. So you can think of modeling an object like that as some surface in R3, okay? Just some three-dimensional surface, which describes the geometry of that particular fox. But if you think about it just for a second, you realize that one surface alone is not enough. The reason is that this object is going to deform. So very similar to what we have seen before in the presentation of Michael. All right? So you have a family of surfaces which represent the same object, and they differ by some deformation. We're going to make a very weak assumption here, and we're going to assume that these two things are related by a homomorphic mapping. Okay? It means just a continuous map from here to there. All right? Now, suppose I give you two figures of the fox, like this and like that. So if you were able to match somehow this mesh to that fox, and the same mesh deformed up to this homomorphic deformation to that fox, then this process of going from the fox image to the mesh, to the other mesh, back to the image, would essentially induce a correspondence between pixels in two images, right? Conceptually, this is how, in your brain, you can tell that this pixel here is in correspondence with that pixel there. Implicitly, in a certain sense, you're doing this conversion process or this translation process in your head. Okay? So this is a model of what's going on. But we can do more because, you know, if you take another animal like a cat, we can still homomorphically map this into that. And therefore, we can use this process to put in correspondence also the ear of a cat with the ear of a dog. And you can generalize this more and more up to some limitations. Okay? So if all these surfaces are just the same, why don't we get just an equivalence class? Some surface here which is equivalent topologically to those, say a sphere, but is much simpler. So we're not committed to any specific shape. So let's do that. We're going to replace the cat with a sphere. That's a spherical cat. And now what we're going to look for is an embedding function which goes from pixels in the image onto the sphere. Okay? with the idea that if you pick 2 points which are in correspondence in the 2 images, then they should map to the same point on the sphere. Now, this sounds a bit crazy. Actually, it's math, right? So if you take this book, well, this is actually a very famous theorem you have in topology, so the Hairy-Ball theorem, which is, at the end of the day, about spherical dogs. Okay, so this makes some sense, I suppose, if you are a mathematician. Probably not so much if you're not. Okay, but conceptually, it does work. So our goal then is to learn a deep network that, given the image X, can determine a mapping of pixels in the image to point onto the sphere. And how are we going to learn that? Remember that we want to do that without manual supervision. We do not want anyone to tell us how this mapping is actually done. So we're going to do it is by training it using either videos or even simpler, using synthetic transformations. So we're going to take the image X, we're going to choose a random 2D transformation of the image, like an homography or an affine transformation. We're going to transform the image like that. And now, if I apply my embedding function to pixel u here, and I apply my transformation g to the pixel, so I get gu there, what is the output of the mapping when evaluated at these 2 pixels? Well, it should be the same because I have chosen pixels that are in correspondence in the image, and therefore, they should be mapped to the same 3D point into this sphericized fox, all right? So I can use that as a training signal in this way. So I'm going to take a bunch of images of, say, cats. I'm going to apply random transformations to them. Then I'm going to train a deep network. The same deep network is trained on the top and at the bottom. So this is called a Siamese configuration for that reason. What a deep network does is, for each pixel, it projects that pixel onto a specific point onto this sphere, with the idea that if you take 2 points which are in correspondence in the image, they should be mapped to the same point on the sphere. Okay? So we are learning to, well, estimate point on the sphere in a way that these correspondences are all satisfied. There's a bit more than that, so you also need these correspondences to be discriminative. I don't want to get into too many details, just have a look at the paper. But at the end of the day, the formulation is just this. It's very, very simple, and beside that, it captures your network that you want to train. It's a simple thing at the end of the day. And this can be done purely unsupervised. All you need is a bunch of images, and then you can apply a random transformation from them. So here are some example results. So very, very simple thing first. So this is a completely toy example. So these are 2 frames of a sort of toy robotic arm. They seem very similar, but they are not. And here is the computed optical flow between them. So these triplets, frame t, t plus 1, and the optical flow are going to be the input to our process. And the output is a mapping that takes pixels in the image and maps them to an unrolled sphere. And what you notice is that as your object is moving here, the pixels get mapped to the same point in the embedding space. It means that the embedding is invariant to the formation of viewpoint. Okay? Now, this is super simple data, and it's just meant for illustration. Here's another one, which is also relatively simple, just to show that this actually work for a 3D-dimensional object as well. So you see here a 3D panda. Again, this is trained using only videos and optical flow. And you see that somehow the network is able to map individual pixels of the panda as imaged onto coherent point onto this spherical embedding, so that you get a correct mapping between the spherical geometry and the panda geometry. Again, purely learned from images without any form of 3D processing at all. Now let's see some real data. So again, in this case, I'm going to use a data set of faces, and the faces are perturbed synthetically, so we know the transformation that goes on because we just invent it. We apply our system, and here are the spherical embeddings that are trained for faces. So you see that the faces in the data sets, they vary quite a lot, but this is somehow able to learn spheres where the key features of the faces are fairly well aligned. It's not perfect, but considering that there is no manual supervision at all in this process, it's still quite remarkable. Okay? And of course, because this is unsupervised, you just change the data sets, and you go for cat faces, and you get these aligned cat masks. Now, the good news, although I don't have slides to show that, there is no time, is that if you take a network which has been pre-trained like this, then it performs very, very well at learning geometric pixel-accurate landmarks of faces of humans or animals if you provide just a little bit of extra manual annotation. So this is purely unsupervised. You add a little bit of manual annotation, then you really nail it, and you get very high-performance facial landmark detectors out of this. Okay? So that's how you can learn some structure of the object in a supervised manner. Let's generalize this a bit, though. So what I've done here is this. I have an image x, I have an image x prime, and I know there is a certain relationship G between them. Okay? Now what I did was to learn a network phi that takes x and x prime and maps that to y and y prime in such a way that these two things, these two outputs, so the network, are related by the same transformation. Now, I'm using a slight abuse of language here. It means that you have defined the action of G in the space where x lives and the space where y lives, and you have a way of making sense of what G means in the x space and the y space. But essentially what this means is that you have implemented a commutative diagram here where the network establishes these two links, and then the same mapping G that works in space x works also in space y, with the crucial idea that space y is much simpler. Okay? Now I'm going to add a little bit more structure to this so it becomes more interesting. So what I'm going to do is to make the assumption that the space where y lives is the same transformation group where G lives. Okay? So I'm going to make the assumption that G and y live in the same space and that that space is a group of transformations. Okay? So y becomes h because that's closer to G in the alphabet. All right? And the assumption again is that the output space of the network is also transformation. So why is that interesting? Because if you do so, then you can take the h's you got here, you can apply the inverse of those transformations to x, and voila, these two things become equal. Okay, you say, who cares? What does that mean? Well, it actually means something very important. First of all, you will notice that before we had this equation, which says, okay, take x, apply transformation G to it, and apply your network. Because the network has learned to be equivariant with transformation, then you can pull G out, and then you can apply G to the output of the network instead of the input, and that works. So you can essentially commute these two operations. Now, if you notice here, this is written in a similar manner, but G is to the right, and I am inverting the output of the network, which I can do now because the network has output in a transformation group. And now you'll notice that G, which is a relative transformation between two data points, x and x prime, has been factorized in the output of phi gx and phi x. Okay? So we call this a factorization process in which a relative transformation has been decomposed into the combination, multiplication, if you like, of two transformations which are determined from each image x and x prime independently. And because phi does not know about both images at the same time, this transformation that is being estimated is somehow absolute. Okay? What does it mean to be absolute? We're going to see that in a second. What does it mean, though? So one first interpretation of that is if you take this absolute transformation and you apply the inverse of that to your image, then these two things are going to be equal. So because there are now these two things that were different are equalized by the two transformations you're estimating, this is also known as a canonization or normalization process. Confused? Well, here's an illustration of that. Suppose you have two images which are related by a viewpoint change, in this case approximated by an homography. So you have x and x prime, same image with a homography between them. We train a network to estimate viewpoint invariant features. This is a topic that was barely touched in this workshop, but basically means that we estimate a region in the image in such a way that if we transform the image, for example, using homography, then the same detection process is going to detect the transformed ellipse. Okay? And this is very useful because if you have a detector like this, then you can match those things correctly once you have them. Okay? Now, we can use our framework to train this automatically. So these two things, these two ellipses, will be related by, of course, the same transformation we have between the images. And if you do what I just said, so you apply the inverse of those two transformations to your image, well, what you get is a canonized image. It means that you're rectifying these two images to something which is shared, a sort of absolute reference point or reference frame, just like the sphere was an absolute frame for dogs or cats. Okay? This is what you get as opposed to the sphere you got before. Let's see a completely different application. Suppose you have two input videos. You're moving around a car with a camera, okay? And you know that the object is either the same or similar, but because the two videos are collected independently, well, there is no obvious correspondence between which frame here best matches a frame there. So the order of them is arbitrary, okay? So suppose now that we want to learn the viewpoint of a car, so we want to learn the concept of car front, car back, and car sides. How can we do that? Well, it's actually quite easy if I give you a single video to estimate relative 3D transformation between frames using, for example, structure from motion. This is almost, I would say, a solved problem in computer vision. So if I give you a single video, estimating the relative motion of cameras in 3D space is actually quite easy. But now we can use that relative transformation to learn a network which puts an absolute viewpoint, attach an absolute viewpoint to your car in such a way that the absolute viewpoints which are being estimated are compatible with the relative transformation you know exists between these two training images. Okay? And again, what you get if you close the diagram here is a sort of aligned 3D space of viewpoints in which essentially all the car fronts are now mapped to the same part of the view sphere, if you like, or the car back are mapped to the same part, and our car sides are aligned. Okay? Sorry. So this was an example of the system. So what you see here is an image which is ingested as input by the network. The network then tells you which viewpoint I think it is. And now here we are plotting a CAD model according to the viewpoint that has been estimated. So if you see here that the CAD model is aligned to your image, it means that the network got it right. And you can see that this works pretty well. Again, without any supervision, you just use structure from motion on videos, and you get that for, and that's crucial, different cars. As before, we were getting this from different people or different animals. Here is another example, something like that working, which is also quite interesting. This is by the Paolo Favaro's group in Bern. They're being extremely successful and creative in self-supervised learning, so it was always a pleasure to read their papers, I have to say, because they have always this quick idea that work very, very well. So here's another idea, which is a bit related to what I just showed you in terms of factorization. So you take an image like that, you break it down randomly into two parts. Say the first part contains one cat, the second part contains two cats. And now you assume that your network is estimating an integer from 1 to k. And what you impose as a training signal is the fact that the sum of the number of things that have been seen in the first image plus the number of things that have been seen in the second image has to be equal to the number of things that have been seen in the image as a whole. All right? It just means that things are preserved even if you chop the image. The number of things overall is preserved. And you can train this, you can use this as a training signal, and it's a kind of factorization because this gives you a sort of absolute count of overall count of what's in the image as a whole, and this gives you counts for individual bits, and now n3 has to be the sum of n1 and n2. It's a bit similar, okay? I'm sure you can see some caveats here. So how do you avoid this problem from becoming degenerate? So how do you avoid the network always predict 0? Well, in order to know that, you have to read the paper. But that's the idea, okay? All right. So, you know what? I'm going to do this. So just a summary slide for part of the talk. So we have seen pretext tasks in the first part, where we want to close this commutative diagram, perturbations, motion, using different modalities. We have seen using equivariance, in which the diagram is a little bit different. So you introduce a transformation you want to regress here by estimating absolute factors. So it's relative transformation. You want to decompose that into absolute factors estimated from each image. What about what you have seen in the previous lectures about generative modeling? So this can also be used for pre-training networks, but it's a little different. So in generative modeling, what you want is you have just images. So a lot of examples of what X looks like. You want to train a model of the distribution of such images. And one way to do that, which is very popular in deep learning, is to start with a very simple distribution, say a Gaussian, and then learn a deep network that takes that Gaussian and maps that Gaussian as a whole by mapping individual samples onto the empirical distribution you want. Okay, it's a way of parameterizing a complex distribution starting from a simple one. You just transform the distribution by learning a transformation between spaces. Now, here you're going to learn one network psi, which is a generator. So the generator takes one of those simple inputs and gives you back an image X. Is that what you want? It depends. So if your goal is to analyze the image, generally you want to go the other way around. You want to take an image X, and you want to go back to some abstract description of the content of the image Y. Whereas here, what we're learning is we have some knobs Y, some random numbers, and by using those and combining them, we're going to get a sample from X. Okay? So the generator itself might not be so interesting for the purpose of image analysis, say object recognition. What you want is to go the other way around. And something like GAN, at least the basic version of GAN, does not really provide this arrow. So maybe you're better off with something like a variational autoencoder, where this arrow is actually trained as well. Okay? So you can definitely use these systems, but some of them might not even give you what you want. Some others do, but they tend to be also very complex because image generation is difficult. And if your goal is just pre-train a model for object recognition, maybe you don't need all this complexity. So it's worth considering those things as well. Plus, this gives you structure, which this doesn't. Okay? I'm going to skip over those things, because that was an example of image generation, but there's no time to do it. I want to move to this part, which I think is a bit more interesting. Okay? Deep image prior. So far what we have seen is what happens if we train a network using a pretext task. Now let's see what happens if you, well, don't do any training at all. Okay? That might sound a little strange, because what do you have if you take a deep network and remove training? What are you left with? Take a network, not training. What's left? So someone was commenting on this before. So it's true that we are using training to determine the parameters of the network, but we are still designing the architectures of networks by hand. Okay? So even before training, there is some, or perhaps a lot, of engineering that goes into designing the architecture of the network. All right? So before training, what's left is the structure of the network. How many filters you're using, the fact you're using filters in the first place, the nonlinearities, et cetera, et cetera. So now what we're going to do is a few experiments on studying how much information there is in the network before you actually do training. And to do that, we're going to consider not the analysis problem for now, but rather the generation problem. Okay? So what we're going to do is we're going to take a small net, well, not a ResNet with 150 layers, some reasonably sized networks. In this case, it has 4 layers, but in practice might have more. This is an encoder-decoder architecture, so it goes from some input noise, which we're going to sample and then fix. That's already a bit weird. Okay? Then it goes through a couple of convolutional layers, and then a couple of deconvolutional layers. That's not the right way of calling them. Those are upsampling, up convolutional layers, or better still, convolution transport layers. Anyway, they just increase the resolution, so there is a decrease and increase the resolution. And then the output of our network is going to be an image. So this is essentially like a generator in a GAN, if you like. Okay? But the parameters of the network here, W1 to W4, are not trained on a data set. They're just free parameters. Okay? And so if you look at the network like that, well, the network just defines a mapping from the parameters onto an image. So you can think as a network as a parameterization of an image. Okay? And again, W, which are your parameters, so far they have not been learned at all. You're just looking at the function, the deep network, as a way of parameterizing an image. So what are we going to do with this parameterization? We're going to use it in the most simple way we can think of. So we take an image X, and then we try to find the parameters that we need to plug into the deep network in order to reconstruct the image. How do we do that? Well, we do that using, say, stochastic gradient descent. So we set this up as minimizing this difference, and then we tweak W using gradients until we reduce this difference to 0. Now here you see the training curves for a bunch of different images. So suppose I put as X, so the image I want to reconstruct is this guy here. Okay? So if you want to solve this, if you try to solve this problem using stochastic gradient descent, well, that's the convergent training curve you get. So that's the loss, and you can see that it decreases quite quickly. All right? So it means that it's quite easy to find parameters for deep networks that do reconstruct that image. Now suppose I add a little bit of noise. You can barely see it here, but I add some Gaussian noise to the image. Then you try to play this game again. Well, it still goes there eventually, so it can still match the input image, but it takes a little longer. Now suppose you want to fit something like a reordered version of those pixels, so you just randomly permute them. Well, you can still do it, but it takes far longer to get there. And if you take just random IID noise, well, it's actually even harder. Okay. So what have we learned here? We learned that if you have a single image and you want to train the parameters of a network or fit the parameters of a network in order to generate that single image there, then if the image looks natural, then the problem is much easier than if the image is just noise. It seems like that the parameterization they have determined by considering a network has somehow a high impedance to noise. It just doesn't like noise. Okay? All right, so that's useful. How can we use that? Well, for example, we can use that for inpainting. Suppose I set up the same problem, but now I only know the value of the image at some pixels, the pixels here. So I delete one every other pixel, okay? Now I solve the same optimization problem only considering the pixels that are visible, but then I plot the pixels that are being estimated and output by the network for the other image locations as well. Well, then I can get inpainting out. So this is a state-of-the-art inpainting method. This is what you get with this method here. It looks pretty convincing, okay? No training, okay? Or if you like, the only training that there is when you're optimizing this model on the fly, on one image alone, okay? Bit weird, but this is not too bad because, well, you know, a lot of pixels are missing, but they are uniformly spread. So what if I create a big hole in the image instead? Well, this is a state-of-the-art method for inpainting. This is what you get using this, okay? No training, bit weird. Okay, let's try to make this a bit harder. So I delete more. And then I'm going to try to play this game by changing the structure of the architecture. So an architecture depth 2 does that. If I increase the architecture, it looks much better. If I use a residual network style architecture, it doesn't work at all, probably is overfitting. And if I use a UNet style network, it gets that, which is somewhere in between. And the best network model we could find, which is not too big of a model, then you get that out. Which, you know, for something that doesn't have any training at all, is not bad. Okay, so what does it mean? It means that effectively, of course, the network is learning about what a book looks like because it sees bits of the books around here. Nevertheless, there is a tremendous amount of prior on the structure of images just in the convolution structure of the network. And it's not just that you do that for a single layer. You actually do need a certain amount of depth for this to work very well. Okay? And that's an amazing amount of information right there in the network from the outset. Okay. Are there any questions so far? Yep. The input. This is a Gaussian IID noise. You just fix it. You can, so if you change it as you're training, then it's just gonna sort of blur things out. I could have also optimized over the input as well. If you do that, it still works. It just doesn't matter all that much. It can be an arbitrary, yep. No, it looks like your standard encoder-decoder network. It's just that if you add more or less skip connections and more or less depth, it performs a little better, a little worse. So it means that the power is really in the convolution structure. Then you can optimize a little more to solve, say, the inpainting problem as opposed to the denoising problem. But I don't think the differences are fundamental. Okay. All right. Now, I started 10 minutes later. So I suppose I can go for 10 minutes further. Okay, good. So I would like to really jump to the third part so that I can give you at least an idea of that. It's going to be quite relaxing. Again, it's a much longer story usually, but I have to cut it very short, so you're going to see only a third of what I was going to show otherwise. Okay? And this topic is understanding deep networks. So what do we have here? So we have a deep network, a big model like, say, AlexNet or SNet. We trained that on 1 million images. We have 100,000 or even million parameters that have been trained. We don't really know what they mean. We know that the network is solving the problem we want, classifying this image as a goldfinch, which is a type of bird, and it works, but we don't know how it does that. So what questions can we ask here? Well, we could ask, what is the network doing? So, okay, it has trained to do something, but what exactly? So maybe we want to characterize specifically what the network does. Then how does it do it? So, okay, it's recognizing goldfinches. Maybe we have determined that with absolute certainty. We still don't know how this answer is obtained as the image goes through different layers in the network. So, you know, this is a very interesting question as well. And then, of course, even if you knew how the network actually does that, you still don't know exactly how this stuff has been trained from data. So these are the 3 big questions I think would be interesting to address. I mean, I'm sure there are more, but these are the 3 ones that are obvious to me. Okay? Now here, we're only going to focus on the first one. So what is the network? What does the network do? What has has it learned to do? Okay. So to do that, I'm going to use a trick or an idea, which is called network inversion. So first of all, I'm going to take a deep network like that. I'm going to chop it off some layer, and that gives me a subnetwork phi. Okay. And so that subnetwork phi effectively is just a map that takes an image x and maps that to some code y. The code y is just a tensor, which is just a high-dimensional vector, effectively. Okay. So it looks something like this. The image is n-dimensional vector. The code is n-dimensional vector. Phi has been trained. I don't know what it does. So it's a black box. How do I study it? Well, one thing you can try to do is to look for how much information there is about x into y. All right. So phi is a map. Therefore, it can only forget information about the input. And so you might ask, OK, what has been preserved or remembered about x at this point into the deep neural network? When code y is computed, what does the network knows about my input image? Okay. Now, why is that an interesting question? Well, because, again, this function is not surjective. It means that injective. It means that it's not obvious, and it's not the case that different inputs will result in different codes. In fact, there are many inputs in general that are mapped to the same output point y. Why do you think that's the case? Why do you think that as we go from the input image onto our final answer y, more and more images are collapsed together to give you the same code? Yep. Dimensionality actually is not necessarily true. In many networks, this is comparable to the number of pixels you have. Invariance, exactly. So you want classification to be invariant to things like viewpoint variations and so on and so forth. So by the time you get to the very last layer, you don't care about the lighting or the viewpoint. You just really care about the fact that there is a cat in the image, and that should be invariant to picking different images of a cat. So there should be a collapse at the very end, at the very least. Yeah. Yes, there is that as well. But those are, I'd say, well, they're adversarials. They're like artifacts of the network. They don't characterize the statistical behavior of the network operating on a normal data set of images. So they're interesting, but they're not my main concern here. Okay. All right, so what I want to do is to characterize this class of images, which we call the pre-images y, that are mapped to the same point, because by looking at what this class is, we can get some clue on the structure of this mapping and the invariances. All right? Okay, so how do we do that? Well, we start from a random noise. We take a reference image x0, we compute the code, and then we stochastically descent, we optimize the noise in such a way that the code becomes the same as the code for x0, and in the process, this is going to drive my input image onto this equivalence class of pre-images. Okay? So we do that through optimization, very, very simple. And this is going to give us only 1 point. So that's another limitation, but it is simple. Is this clear? So I'm going to repeat it because this is very important. So I start from random noise. So this doesn't have any knowledge about x0. The only knowledge which is obtained is through the code y. Okay? So you want to match these two things here. And you do that using stochastic descent to change the input noise in such a way that two codes match. And here you get an image as output. Now, these two images are exactly equivalent, or nearly equivalent, from the perspective of the network, because this code is nearly the same. But in general, they look very different, meaning that there are many images that are mapped to the same code there, and that gives you information about the invariances of your model. Okay? So I want to do this. And if I play this game and I don't pay attention, what I get actually are artifacts. So if you just pick any point in this pre-image, you can still see a bit of structure, but it's very, very noisy. If you were to do this inversion, not on an arbitrary space of images, which an image here is just a bunch of numbers, but you restrict yourself to the set of natural images, then your inversion is likely to look much more realistic. Well, it will look more realistic because it's going to look like a natural image, but it's also going to be, is likely to look more like the image you're trying to invert or reconstruct. Okay? But and this makes sense because the network has not been trained to operate to do anything meaningful outside the space of natural images, because the network has been trained on those images, not on those images. So this is actually OK. But if you want to optimize over the space of natural images, that's actually very hard because we don't know how to characterize that. So what we end up doing is using some sort of pseudo-natural image prior. And we want this to nudge this inversion process to give us something which is a bit more natural, not as full of artifacts like this one. So we get something which is a bit more interpretable and something which is more likely to characterize the natural behavior of the network on the space of data it has been trained on, which is what we really want to understand. Okay? Now, this is an example where we're just penalizing some high-order coefficient in the Fourier domain, or just derivatives, in fact. Okay? What kind of priors can you use? Well, there are several. You can use, like in that example, something like the TV norm. Just basically means penalize derivatives in the image. You can use, which is just, it means that your optimization problem becomes something like regularized risk optimization. Or you can constrain the space of images you can generate. And we're going to see that in a minute using this deep image prior idea. Or you can try to model this probabilistically, putting a very strong prior of what a natural image looks like. And there's a lot of interesting work done there as well, which, if I have time, I'm going to review in a bit. Okay? Although I only have 4 minutes, so maybe not. So I'm going to focus on that. I'm going to show you the main results. So how are we going to use our deep image prior to regularize this inversion process? Well, it's actually quite easy. So you have your input image, the one you want to invert. Compute feature, these are your features you want to invert. You plug in here noise, this goes to the same feature extractor, and you want to match y naught with y, and use stochastic linear descent to optimize this difference, okay? Just as we have said. But now, X is not just a bunch of pixels, it is the output of a deep network that crucially, and that's very important, does not have any training applied to it. Just, for each image we want to invert, we're going to initialize this randomly. So there is no information which is transferred from a prior data set into the process. What you see, whatever structure in the image you see, is essentially the result of those weights which actually have been trained on a data set like ImageNet. All right? It's not information which is encoded in the prior, except for the structure information they showed before. Okay? So formally, it's very simple. You just solve the same problem, but now X is replaced by the output of psi of W. But W are the parameters of your network. I'm going to apply that to AlexNet. So AlexNet has many layers, and I'm going to chop it off at each layer and do the inversion process. And so this is what you get. So take COM1, invert it. This is the original image. That's the inversion. They are nearly identical. What does that mean? Any courageous individual want to guess what this means? So if I can take my image, compute COM1 features, and then I can invert them back, and I get that, what does that tell you about the amount of invariance that there is in COM1? Do they look similar? You should be able to answer that. Do they look similar? Good. OK. So it means that there is very little information lost. It means that there is very little invariance that can be detected in COM1 using this technique. Okay? It also means that the output of COM1 as a whole essentially contains almost perfect information about all your pixels. Now, as we go deeper, you'll see that the image starts to deteriorate. Okay? This is COM2, COM3, COM4, COM5. So you see here that the image is a little bit blurry. What does it mean? It means that, first of all, it's very important to understand that if you feed to your network this image or that image, by the time you get to COM5, the code that you get is, for all practical purposes, is the same. Okay? So the network at this point cannot distinguish between these two things. It also means that you get invariances to like small jitters of local structures in the image. So you see that the eyes are a little different, so you can shift position a little bit and so on and so forth. Okay? Now these are convolutional layers. Now we're going to jump to the fully connected layers, where we're going to. What do you think is going to happen when we do the jump from COM5 to FC6? It will break the spatial structure more. So now the monkey has 3 eyes. Okay? And if you go deeper down, it breaks the structure even more, and more. Okay? And this is barely recognizable as a monkey. In fact, it's not recognizable as a monkey, I would say. However, and I don't have time to run the demo, but if you were to, in real time, show this image to a network, it will say, well, that's a monkey. Okay? Quite interesting. It's like an artifact that makes the monkey concept fire. And here is a summary slide where you see the progression of how information is being somehow lost in this coding process. I want to show you something a bit more interesting, which is the same process ran on a video of like, I think 8 minutes. Took a week on GPU farm to do this. So I need to show you too, okay? Also, you have turtles, so very appropriate. Anyway, so what you see here is the input frames, and then these are the inversions from COM5. And again, you can see the sort of jitter occurring. The reason why you see all these little vibrations is not because the method is bad. The reason is that each frame is reconstructed independently, and therefore is going to land on different samples of this pre-image space. Now, that means that the more changes you see in these images here, the more invariance the network is capturing. Okay? And so if you go to FC6, you see there is a lot more invariance. And if you go to FC8, that's even more dramatic. Okay. But now, well, that's just, surely it's longer than that. Anyway. So now, one thing I would like to note, well, this is actually pretty obvious here. So this is very, very weird. When I saw that the first time, I was very perplexed. Why is that? So think about it. This is AlexNet. FC8, the output of FC8 is 1,000 numbers. And those numbers are the score that each of the 1,000 classes of ImageNet is assigned to by the network. Basically, it's a classification score. What this means is that in theory, what should happen at this point is that if there is a monkey in the image, then the filter, the neuron that says monkey, should fire up a lot, and all the other ones should be very low. So there should be no visual information. There should be only semantic information in principle. But if you do this inversion process, starting from FC8, I mean, you can still recognize a lot of the structure that are in the image. This is very visually specific, right? What does that mean? I mean, these are just inversion of classification scores. Why does he know about a wave? I mean, a wave is not even an ImageNet category, you know. Why does he know about turtles seen from the top? Bit puzzling, right? It is, and I don't really have a super good answer about that. It does not mean that the network is failing to classify your turtle. It just means that in those numbers, overlaid to the class information, there is still a lot of visual information. But that's not entirely surprising because your network was evolved by not knowing what classes were. So presumably at the beginning of training, visual information was propagating throughout the network, and the network doesn't really kill completely the visual information to be perfectly invariant. It just kills enough so that it can answer the classification problem correctly. But maybe this is what allows the network to train, because even so deep down, there is still information about the image content. Just a conjecture here. Okay? All right. Now, do we have more time? I guess this is probably... So I talked about 3 things. I should have talked about 3 things. Unsupervised representation, no time at all, so I skipped over that. Unsupervised representation, self-supervision for learning features, self-supervision for learning structure, and this deep image prior as an attempt to studying what's in the prior that you get when you just design a network before even training it. And then I discussed a little bit understanding representations, more than understandable representations. And so we covered visualizations. There is another very popular and useful thing you can do, which I think could be quite useful in medical imaging. That's called attribution, determining which part of an input image are relevant for the prediction the network is making. So if you want to detect cancer in some medical data, then maybe that can tell you where the network thinks the cancer is actually located. And then semantic identification, which is to try to find, to name the responses of neurons or a combination of those responses with things which make intuitive sense. So you can interpret the activations throughout the network in a way which can make sense to a human engineer, essentially. Okay? So these are just a very high-level overview of several things I think are very important. I don't think we have super good ways of doing any of them. I think people that, like René, that are doing a lot of theory deep networks, once they are done with it, they're going to improve all these sort of things which are more realistic tremendously. In the meantime, I hope we're going to help them by providing some hints and clues on what could be interesting to look at. Just one last thing. So if you want to know more about this, I'm going to upload on the network a complete set of slides which has all this part which was completely missing, as well as these two parts as well. In the case you want to have references, there are lots of them in them. Okay? So thank you very much, and if you have questions. There's one question by...
Okay, I will start. So
yeah.
You mentioned you use a pretext representation, a task to help the target task, but I don't see any results on the target task.
You don't see any?
I don't see any results on the target task.
Yeah, so I didn't include them, but this is a very fair point. Just because I wanted to cover a lot of concepts, and I didn't really have time to show too many results. So in an extended version of these slides, I would have definitely did that. But so the question is, okay, so we do this, or at least I think the question is this. So once you have done this, so we've done our pre-training, then we need to transfer the target task. So how well is this working? Yeah, maybe I should have had at least one slide on that. So the answer is as follows. If you do this, so a typical test setup is you pre-train on some pretext task, and then you transfer your feature on ImageNet, and you see how well Conv1 pre-train, Conv2 pre-train, Conv3 pre-train do, compared to what you would get if you were to train this network straight from ImageNet using all the supervision you had. Okay? So you just try to replace parts of the ImageNet network with parts which are being pre-trained without supervision. And then you compare how much of a gap there is between full supervised training and full unsupervised training. And the answer is that Conv1 is essentially the same performance, so it doesn't matter if you use one of those pseudo-tasks or ImageNet, you get essentially the same. Conv2, almost the same, as well as Conv3. In Conv4, the performance of the gap starts to become larger, and in Conv5 is actually quite large still. Now, having said that, every month, a new paper on this topic is coming out, and the gaps are closing very, very quickly. So to give you an idea, so in Conv5, if you apply linear classifier on top of that, and you pre-train everything in ImageNet, you might get, say, 55% accuracy. If you were to do that using unsupervised Conv5, you would get 48. So instead of 55, you would get 48. So there's still a gap, which is substantial, but it's not 100%. Okay.
Thank you for this fantastic talk. I had a technical question about your example with cats. Basically, embedding into a sphere is ambiguous. You have rotation. Is it a problem, or you don't care, and maybe if you run the same network twice, you will get the same cat embedded into a sphere at a different place?
No, you must not, and you can't not, because if you did that, then, let's see, I should, so this is the disadvantage of doing animations, I guess. Too many. Where is it? Yeah, this. So if you don't map corresponding points of these two pairs of cat images, so if the eye here was mapped in a different part of the sphere, then you will get a loss there, right? So it has to learn to map the cat points to absolute points on the sphere. So it's learning, it's like trying to put onto the cat face an absolute reference frame. And this is because while the information is relative, the information there is, so G somehow connects image 1 to 2. Each network here operates on an image alone individually, so it doesn't know about the other image. So to make this commutation work, it has to estimate absolute location for those points. And this is how this really works. Another thing is that for training here, we only use pairs which are related by a transformation, so there is not much visual difference between those two. But in fact, if you apply now to a different face of a cat, the alignment still makes sense. All right? So it's even able to somehow jump between different cat species or different cat instances. And that is through smoothness of the network, I think.